Greetings and welcome to the Mothership, the Mothership Connection. This is Calculus in the PM, in case you've just joined us. Today, 2.1, rates of change, limits, etc. And this is our fourth part, our final part, and they're the limits that involve trig functions. Before, we said we could always use a chart of values and get closer and closer to our desired value, see what it looks like it approaches. We could use a graph to do that. We could also algebraically manipulate. Now, trig functions, you can't factor stuff. You could use some trig identities sometimes to manipulate them, but it doesn't work the same. Now, I have this sheet here, and I'm not going to go over it anymore. I used to, but then, you know what? Felt the educational purpose of this. If I go through it with the sine and cosine, whatever. I have a link here that still exists there, but I have this information from this. If you wish to look through it, go ahead. Here's what you need to know about a squeeze theorem, and then I'm not worried about how it's applied here. I used to go through it, like I said. But the main thing is this squeeze theorem, and this is from the Cosine textbook that I referenced earlier. If the function g is considered smaller or equal to the function f, and that function, same function f, is smaller or equal to the function h. So you know what I mean? We got it ordered. First, second, third, right? Lowest to highest values in the function. So here's my h, the highest values. Here's my g. Now, in the vicinity of some value x equals 0, x equals c, x equals 2. And here's my c on the picture. And if the limit of g, or x approaching c for the function g, is equal to h, the value when you plug in c for that one. Got it? So this is the h function. Oh, I drew it a little wonky there. And this is the g function. And they meet up, is really what we're saying. They're equal there. Well, doesn't it make sense? We've sandwiched the value that must be for the middle function. If the upper and the lower are equal, that's where the function in the middle must have a value. That's what we're saying. Therefore, then the limit. We've sandwiched it. And that's the idea. It's a simple enough idea. We go through it, and this is where sines and cosines come up with these limits. And you'll notice that it's falling down, actually. I have it up from last year, but there's some sine trig stuff. But enough about that. What you need to know out of this next page. Results you need to know? These ones. And I'll talk about them, because really, there's only two things. The rest are just variations of those two things. The first thing you need to know is the limit of theta approaching 0, if it's sine of theta over theta. Well, the first thing you'd naturally do is try to just plug it in and see if it works. What's the sine of 0? 0, right? And 0 over 0 then, how's that going to work for you? That's indeterminate. That's why you need the sandwich theorem to do this, figure this out. When you do, it comes out to be 1. And there's another method too that later on, as far as you're going to say, do I have to memorize this? Not for this chapter exam, because I'm going to test you as if you're a Calculus 30 Saskatchewan student. As far as AP Calculus and stuff, by the time you write the test, there's going to be something called L'Hopital's rule and stuff. You'll be able to do something like this anyways, without memorizing this, if you need to. And it will come back to you, but don't worry about that. So, you don't need to memorize this result. It's handy to have it, but anyways. So this result here. Now look at this. As long as it's the sine of the same thing over the same thing. You follow this? Theta over sine of theta over theta, that thing. So if I said sine of 30 degrees over 30 degrees, well, this isn't approaching 0, I guess I wouldn't say 30 degrees. But what if I had it then as the theta, instead of theta, I replace it with kx and kx. Isn't this the same thing? That's what I'm saying. This is the same rule once. So I'm going to give you this rule in one form, like this. But it's really the same thing here. What about this? This is the reciprocal. it makes sense that that would also be 1. The other one that you need to know is 2 variations of the same thing. I think you can clearly see why they're just multiply by -1 and that this turns into this, right? And if it's equal to 0, it doesn't matter if you go cos of theta minus 1 or if it's 1 minus cos of theta. For this limit, it is 0. Okay? Now, evaluate each limit here. Let's see how this works. We have to turn a into. So I'm going to use this rule because you can see right away it involves the sine function, right? So it's that rule. Sarah, you're very tired. Do you want to go up just down the hall to wake yourself up? Okay. Zach, I noticed you earlier, but I was going to suggest the same. Okay, it has been a long day. I don't mind if you need to energize yourself. Okay, I'm going to write this down. The limit of x approaching 0 x over sine 3x. Now, first of all, I don't think it confuses us because it's the reciprocal, it's upside down. But what has to happen, whether you think of it as in this form or this way, is that this theta has to match this theta, and that's not the case here. Question. Can I just divide out the 3x like that? Like, can you do that? No, you can't operate inside a sine function or a cosine function, inside a function. So my question is it easier for us to use trig identities to change this 3x sum out of x, or is it easier to work on this one and change it to 3x? It's the top, yeah, because you can do that algebraically. So what we're going to do is we need a match. So if I multiply the top by 3, we've got a match. I'm going to use a different colored pen to show us. Now, if I multiply this by 3 out of 3, would you agree then? My next step. I haven't evaluated the limit yet, but I'm only doing this to show you where the 3 came from. I moved the 3 over. It's the commutative properties of multiplication or whatever. 3 times 1 is the same as 1 times 3. However you want to think of it. 1/3 times 3 is the same as 3 out of 3. I guess. Anyways, do we have an exact match to the rule now? Here. Yes, we do. It's the same thing that's inside the sine function, right? As long as we've got a match. So what is that? What does this limit part turn into? According to the rule? It's 1. And then the 1/3 is left behind. It's 1 times 1/3. Do you guys follow that? I'm going to write it out explicitly this time. Equals, now I wouldn't normally do this, but I'm instructing, so I'm telling you guys, 1 times 1/3. Now I would expect you, after you've done a few of these, to just say 1/3 is the answer. I'm moving it down a bit. But what I do want to show your work is a step. I'm going to be looking for this, okay? Sometimes people get the answer, the right answer, for the wrong reasons sometimes, because we tend to use so many small numbers like 1 and -1 and stuff. Anyways, so I need to see that your work was done correctly, you were thinking correctly. Because I'll show you, and I hate to show you mistakes, but this is where people make mistakes in thinking. I'm going to erase this soon after. It's adulterous, it's terrible. You know this. Okay, so somebody says, okay, this is easy. I just divide out the 3 and I've got this. You follow me? I made a mistake. You can't do this, right? you're getting the right answer for the wrong reason, though. Because is this valid? No. And if you want to ever try, you can't do that. Right? Like, you just take something like, type in your calculator. Well, the sine of 90 degrees. What if you divided that by 3? Well, you got 30 degrees. The sine of 30 degrees, like, and does that have that times 3 property? No, it doesn't. You can't just take out. Anyways, that's rubbish. Don't do that. Okay, like I say, I hate showing mistakes, but I've seen that one too often. Okay, the other one. Sine of 5x over 6x is what I'm limiting. Okay. Okay, this is sort of like a doubled up problem. Now remember, whenever you're doing these, make sure, okay, it's x approaching 0, and I can't put sine of 0 over sine of 0. 0 is 0. Right? Indeterminate. I've got to use this rule. But if somehow I had given you sine of x approaching pi quarters or something else, you could just do this and just calculate it. No manipulation, okay? Always keep a mental check beforehand. Now, I think of this similar to the red problem here, sine of 3x. Now, maybe I'm going to just use 2 colors for this, just so I can show you how I'm organizing. Was that 6x again? Yeah. Okay. Yeah. Now, think of it this way. I'm going to write it out longer than I normally would, because I'm going to show you my thought process this way. The limit of x approaching 0, I think of this as sine of 5x times 1 over sine of 6x. Would you agree I haven't changed a thing? I'm just rewriting it in a slightly different way. Why? Because maybe now I can think of this differently. There was some limit properties and stuff that I mentioned. Check in the textbook, see if they make sense. Well, one of them is that you can kind of like distribute it, sort of like. Then it's the limit of the sine of 5x times the limit of this expression. So we could treat this as if it's 2 problems, but we're going to write it out as 1. Now, what's missing from this sine of 5x here that would make it easy to... yeah, the 5x here. And this one, likewise, is missing the 6x. So, what do I really need to multiply by to make this thing work? Well, let's just put this in here. I need to multiply by, I'm just going to, 5x over 5x, correct? Yeah. Now, I'm going to do something here. I'm going to just insert this here. Now, no, I'm going to show my work for you. And likewise, I need 6x over 6x.
So you're counting everything twice?
Why am I doing everything twice?
Because you broke the equation.
I'm sorry?
Because you broke the equation.
Okay. And I'm treating the black problem and the red problem separately. Okay, I see what you mean by twice. Okay. Yeah, I'm fixing the sine of 5x with the 5x. What I was going to do all in one step, and what I typically do is, I write this out here. It doesn't matter that the 5x and the 5x are separated, right? And then I typically, okay, this one got stuck together. I even picked up the marker. But what I'd do is then 6x. I'd say, well, I'm going to make this just one fraction of this here, right? Does this make sense? I would show this as one step, but I was instructing, so I made it long. So this would really be my second step. Make it your third step, because don't erase what you had. It was all right. I'm trying to show you your thought process. By the way, on this 5 out of 6, are these x's necessary anymore? No, they cancel out. showing the thought process though, so that's why. I would have had it shortened to this. So this is what I would expect as work to be shown for this kind of question. Now, this is a walk in the park. Okay. Once I got it to the stage, getting here. It's the new skill. So with this one here, this turns into, when I apply the limit, 1. And this turns into 1. And this doesn't turn into anything. It's 5/6, and it still is 5/6. So overall, 5 out of 6, right?
So didn't the limit apply to the last one too?
Well, is there any variable in it though?
Oh,
It's the limit of a constant. The limit of 5/6 is 5/6. So, yeah. Okay. So you can't divide out the 5 in 5x, sine of 5x. Keep that in mind. You will screw up somewhere if you do that, and it's wrong. Now, how about this puppy here? Evaluate each limit here. I got a tangent function. Well, there's a few things you need to be aware of. Trig function-wise. The only, you don't need to know your double angle identities and your half angle identities and sums and stuff like this. If you need those, they'll be given in problems. I see no evidence in AP exam outlines and stuff that you need to know those. You do need to know the quotient identities. The tangent function is the ratio of the sine over the cosine function, right? And then cotangent is the cosine function divided by the sine function of x, right? You do need to know the reciprocals. For example, with tangent is 1 over the cotangent, or vice versa. You could say secant is
Secant is 1 over
cosine.
Yeah.
Yeah, those are reciprocals, and sine and cosecant are reciprocals. The other thing you need to know then is the Pythagorean theorem. Cos squared of theta plus sine squared of theta equals 1. From that, you can get the other two. More about that when we need them. Okay. Back to this. So the tangent function, I see it here, and I say I only know about sines and coses, so I need to manipulate. So the limit of x approaching 0, as soon as I see this, I'm thinking sine of x over cosine of x. And I'm not, yeah, sine of x over cosine. I'll do it in 2 steps. I was going to skip some steps. Gotta slow down. Now, does it confuse you? Because I don't like triple fractions, meaning I don't want to write it like this. I just think it looks stupid. So, I like to keep it at least, it's no different to say divide by 2x as 1 over 2x, right? Okay, that's all I'm doing. Now let's do some old switcheroo stuff so that we can just, the sine of x, okay, the cos of x actually isn't a problem, because what's the cosine of x as you approach 0? Cosine of 0? Naughty, naughty, yeah, okay. Just remember this. A cosine function from 0 to pi is a sideways c for cosine, right? Can you just see where the cosine is? It starts at 1. Now, I'm not labeling this, but this is, I guess. And the sideways s would be for the sine. It's just a coincidence. In another alphabet, it wouldn't make sense, would it? So.
Is cos and sine, like, are they cos and sine in other languages, or are they like
Okay, are they cos and sine? Sorry, your question?
in other languages? Like, do they have?
Ask someone who speaks another language. Did you guys use the words sine and cos? You didn't have, you did. Because which language did you speak?
Oh, we did it in English.
Oh, you did it, you did your math in English.
Yeah.
Tagalog is not, they didn't, you did in English, okay? French, the Sion and cos. I don't know.
Sion and Cosine.
Cosine. I don't know.
The same, but like with different.
But I'm sure in another, yeah, I know what you're saying. And yes. Okay, anyways. what do we need from this? I need the x or underneath the sine function of x, right? I can leave the 2 out here. I really don't care. Actually, that confuses things if I move the 2 there, right? So all I'm doing is reorganizing my thinking so that Shindalik is convinced you know what you're doing. I'm not actually doing any work here other than an exercise in futility, you might be saying. This is the same Shindalik. Now I'm going to move the cosine of x beside the 2. And it's fine. Now, when I apply the limit, we know that the bracket sine of x over x is 1. And that's the rule. Got to follow the rules. The other one, 1 over 2 times the cosine of x, as that approaches 0, it's 2 times 1, isn't it? You guys follow me on that?
Wait, why does the 2 and the x get split up when you use the quotient?
Okay. This right here.
Yeah.
I'll just ask you a question here. Is 5 times 3 the same as 1, 3? Now this isn't an x, this is a multiplier. Okay, I think you'd agree with this, right? 2 times x, x times 2. Oh, okay, I don't have them separated, but you see, I'm just moving the placement of the 2x, the x and the 2. To make it look, it's really to help you. You could evaluate right here. Just saying, yeah, this x, this sine. Okay. You got it. So, this is 1 times 1/2. Again, right? Because cos of 0 is 1. So, there we go with that. The other rule is actually, I'll erase my 1 over 15. Multiplication is commutative. It can commute, it can move around, it can travel. That's what we say. Okay. This looks like it's applying this rule. It looks like, doesn't it? First, double check. Can't do it just as it is because I got 0 over 0. 1 minus 1. Any hunches? Yeah. There's 2 ways I could think of doing it, and you got to change the top around, and what do you see right away? You could do one way with it strictly algebraically, meaning not using a, what's the apparent factoring for the top? It looks like a difference of squares.
0, so anything multiplied by 0.
Well, no, you can't. I'm not sure then what you're saying. Maybe I'm thinking what you said doesn't apply. I'll change colors just so we don't run into the black. X approaching 0. So if this was 1 minus b squared, it'd be 1 minus b, 1 plus b. Well, this is 1 minus cosine squared x. So 1 minus cosine of x, or x in this case. 1 plus cosine of x. I'm going to put this one over x because remember how the other form of this looked like this, didn't it?
Don't put the other one over x too?
You could, but I'm trying to organize my thinking so that this looks like the rule I'm trying to apply. That's the only reason why. It is all over x. That's the same because it's multiplying on the numerator. Yep. However, I'm only looking at this part because that's the trouble part, because that's 0 over 0 still, isn't it? Can't do 0 over 0. But once you have it in this form, which is a variation of 1 minus, you remember on the other page we had the rule the other way around? Okay, so we've got 0 for this, and this, is this valid? Sure, it's 1 plus 1, it's 2. 0 times 2, I'm going to write that out this time. 0, 2, but it still turns out to be 0, okay? Now, the other way of doing this is, what was the Pythagorean theorem?
C squared plus C squared.
Sine squared plus cosine squared equals 1. And it is a squared plus, but that comes from the unit circle, a squared plus b squared. Okay, that's where the sines and cosines are. So, 1 minus the cosine squared would be sine square x, you'd think, right?
Yeah.
Okay, so one of those sine x times sine x is what sine squared means. So you would have a sine of x over x, which is 1. But then you'd still have the other sine of x side. And that would turn out to be 0 when you plug in x equals 0. But it's fine to do it that way because it's only on the numerator. I'll stick to this method for now. Okay. I'm trying to give you guys work time, so here. Now, I said try every third one. 3, 6, 9, 27. These, there's nothing in the textbook to try. I have the answers listed for all of them on here. But that's enough if you do it that way, okay? And let me see here.
Are we doing 30 and 33?
What's that?
Are we doing these questions too?
Oh, yeah, right. Let's just take a look here and I'll double check if those are. Sorry, I flipped too much. Flip my lid. 30 and 33 from page 66. 30 through 33. Those are done by a graphing calculator anyways. Did I already assign them? Because somebody asked me about 31 anyways, eh? So I already had those, I guess. But yeah, make sure you did do those. But use a graphic calculator to look at those. And then you can try to apply your new rules, right? If you wish, you could do those either way. You're getting plenty of practice with sines and cosines. One last note. When you look at some of these, you scan, most of them are x approaching 0. But if you ever see one that is x approaching something else, okay, infinity, what's it going on to do forever? Or else pi halves. Check first with pi halves. Can you just plug that in? You're darn tootin' you can. That's not 0 over 0. You know, stuff like that. Okay, these ones, most of them are approaching 0 though. And then infinity. If you were to graph, the way to do the infinity one is to think it through or do it by like, if I was to graph that, what would that look like? Just think about this. Actually, I'll just tell you about this one right now. Sine of x. As you go on, if it was just the sine of x, don't worry about, as you go on to infinity, what does it look like? Up, down, 1 to negative 1, 1 to negative 1. It never varies outside of that range. 1 to negative 1. Sometimes it's 0. What about the bottom? Pick a number as you go up infinity. Pick me a big number. I don't care. 12, eh? I'm 12 years old. I'm a big boy now. No. Like 1,000 or something like that, right? Now, at most, sine would be 1. What's 1 divided by 1,000? It's pretty close to 0. What's negative 1, because it could be as low as negative 1 divided by 0? Negative 0.00. Okay, it's very close to 0, isn't it? And it's just going to keep varying very minutely from 0.001 to negative 0.001 when you get up to 1,000. And it's going to hit 0 in between. Now think this through, but the graph, sorry, I was doing cosine. Cosine, the same kind of story, but it'll go like this, and like this, and get smaller, right? So what is that approaching as you go off into infinity? 0. Yeah. You can think that one through. I've thought it through with you. Anyways, work away.